will be hosting. I will be the host tonight, but because my limited background on the cancer genomics, so Mr. Sung, Dr. Sung from our team will help us at the Q&A section. Is it okay? Is it fine for you?
Okay.
Okay, thank you.
Well, it's so great to see you today. My name is Seth, and I will help to translate the Q&A session to you and the audience. So hope that we have a good session today.
Yeah, thank you.
Okay, but is there anyone else from your side, Dr. Lu? Is there anyone else from your side? Dạ, có anh chị nào bên phía SURAN không ạ?
Hi, this is Jason.
Jason?
Yes, from GeneMind. I'm a product manager.
Okay, thank you. Do you
Nice
have
to meet
any
you.
presentation today or only Dr. Liu?
No, only
Okay,
stay with
okay.
Dr. Lu. Yeah.
Okay, thank you. Please help to support or supplement anything or highlight anything if when you feel needed, okay?
Yes, of course.
Okay, thank you. We will wait until 8:05 and then I will introduce a little bit and Vietnamese to the participants. Dr. Liu, do you want to check your screen sharing to make sure it works well?
Okay, I will share my screen.
Okay.
Could you see my slides?
Still, yeah, I can see it. Great. Can you share your full screen and move to the next slide?
Is it okay?
Yes. Okay, thank you. Okay.
Chắc chắn.
Ninh Trần Vinh, Đào Lê Bạch.
Recording in progress.
Ờ, kính chào các thầy cô, các anh chị, các bác sĩ và các bạn. Chào mừng mọi người đến với buổi học tiếp theo của khóa học Bioinformatic Analysis for Cancer Genomics. Buổi học hôm nay sẽ diễn ra từ lúc khoảng từ 8 giờ đến 10 giờ tối. Diễn giả ngày hôm nay sẽ là Dr. Qin Lu, là Senior Medical Manager từ cái Department of Applied and Translational Medicine của China. Thì ngoài ra còn có cái sự đồng hành từ Mr. Jason Zhang là từ công ty SURAN, là nhà phân phối chính thức của GeneMind tại Việt Nam. Buổi học hôm nay là sẽ xoay quanh những cái giải pháp toàn diện của công ty GeneMind trong Cancer Genomics, từ cái khâu mà tách chiết acid nucleic, chuẩn bị thư viện, bắt giữ mục tiêu cũng như là phân tích tinh sinh học. Em giới thiệu một chút về cái công nghệ của GeneMind. Thì GeneMind là công nghệ giải trình tự đoạn ngắn short read dựa trên là sequencing by synthesis, tương tự như là Illumina. Ưu điểm của công nghệ này là có cái độ sâu giải trình tự rất là cao, cũng như là độ nhạy vượt trội, cho nên là nó sẽ phù hợp với những cái loại phân tích các cái mô như FFPE, sinh thiết lỏng hoặc là MRD. Ngoài ra nó còn đặc biệt hiệu quả trong phát hiện các biến dị nhỏ như SNV và indel. Để mà em xin phép so sánh một chút với cái công nghệ PacBio mà mình đã được giới thiệu từ tuần trước, để mà các anh chị có cái nhìn tổng quan và rõ ràng hơn, cũng như là có cái sự so sánh khi mà mình sử dụng ví dụ như là PacBio Hi-Fi thì nó sẽ giải trình tự đoạn dài, thì nó sẽ phát hiện tốt những cái biến dị cấu trúc lớn và cũng như cái vùng gen phức tạp mà cái short read từ bỏ sót, cũng như là isoseq. Nhưng mà cái nhược điểm của nó là chi phí nó rất là cao, cũng như là nó cần cái lượng mẫu chất lượng cao hơn. Thì ví dụ như mình lấy cái cục mẫu nó phải to hơn thì nó mới giải ra được cái kết quả tốt. Thì đó là một trong những cái khuyết điểm của họ. Thì tuần rồi người ta cũng đã có cái giải thích, có những cái giải pháp khắc phục. Ví dụ như người ta bỏ cái hóa chất vào, hoặc là người ta có cái protocol để hiệu quả, nhưng mà mình vẫn phải tốn thêm tiền để mình mua cái hóa chất đó. Cho nên là thì em có đưa ra một số cái so sánh nhẹ nhẹ, nếu mà anh chị mình đã học cái buổi tuần rồi, để cho mình có cái nhìn tổng quan và cũng như có cái insight về cái trình tự. Em cảm ơn mọi người ạ. Cũng như là tuần rồi tại vì là nếu mà anh chị nào có thể giao tiếp hiệu quả bằng tiếng Anh thì mình đặt câu hỏi trực tiếp luôn đến là Dr. Liu để mà cái câu hỏi mình nó rõ ràng hơn. Hoặc còn nếu anh chị nào không trả lời trực tiếp được bằng tiếng Anh, không hỏi được bằng tiếng Anh, thì tụi em có thể hỗ trợ, nhưng mình cố gắng mình diễn giải câu hỏi nó ngắn gọn và nó dễ hiểu một chút, tại vì tụi em sẽ dễ dịch hơn. Em cảm ơn ạ. Dr. Liu, please share your screen. You can start now.
Okay, thank you for the introduction, and thank you for the invitation. It's my honor to share my lecture and our solution skill. Today's topic is the solutions and the bioinformatic pipeline for the oncology from GeneMind. And my lecture will be in two parts. The first part will be the bioinformatic pipeline for oncology, and the second part will be some detailed introduction for our oncology solutions. And let's begin the first part. And here is an overview of our oncology solution workflow. We do the nucleic acid extraction, the library preparation, the sequencing, and the data analysis, and then finally we got a clinical report. It takes around 31 to 68 hours in total. It depends on the data volume and depends on the platforms we use. Here is the overview of our bioinformatics pipeline. First, we got the input data of FASTQ files of read 1 and read 2. Then we do the alignment we do the alignment by the BWA. It's a very common used software for the alignment. Then we mark the duplicates and we do the quality control. We have some GeneMind SNPs for the chemotherapy and for the contamination quality control. And then we do the somatic variant calling. And we do the annotation for this variant. And we do the filtering. Then we call the CV, the MSI, and the fusion. Also, we could do the HLA genotyping. The HLA is associated with the treatment outcome of the immunotherapy. And we could have some panel do the HRD analysis. Then we collect all the analysis results. We do the manually review, and then we got the finally report. And this procedure is fully automated from the raw sequencing data to the genetic test report. And all these modules is very flexible, and SNV, CNV, Indel, SV, HRD, and MSI could be detected. And we have the gorgeous QC for the cross contamination and for the gender verification. And our system is very fast. It's used the GPU speed up, and we could finish all the process in 15 minutes for the small panel. And for the big panel, we could finish in 3 hours. It's very fast. Here's some basic principle for the FastQ quality control. This is a picture for output by our sequencer for the ratio of the base of the ATCG. And we could see the balance of the base. The A is complement to the T and the C is complement to the G. So we need to see the A ratio is similar to the T and the C need to be similar to the G. As we see from this picture, the base is balanced. It's very important. If the the base is unbalanced, maybe something is wrong with the sequencing. So maybe the library should be resequenced. And another very important quality control metric for FastQ is the quality score, well known as Q30 or Q20. The sequencing quality score is defined by the following equation. It calculates by the -10, multiple log 10, and the error rate. If we got Q20, it means that the error rate is 1 in 100. The accuracy is 99%. And if we got Q30, it means that the error is 1 in 1,000, and the accuracy will be 99.9%. And if we got Q40, then we had 1 in 10,000, and we got an accuracy of 99.99%. It's very high accuracy, and we could see that this is an output from our sequencer. And this is a characteristic of the features of the SBS. As the sequencing goes, the Q30 decreases. And we could just look at the out data Q30, and we could see the output of our sequencer. The Q30 is over 90%. It's very high. And another quality control for FastQ is the GC content. The GC content means the ratio of the GC of the FastQ data output by the sequencer. And we could see in this picture is the distribution of the GC content across the human genome. And we could see that the mending GC content of the human genome is around 42%. So if we do the whole genome sequencing, the GC content needs to be around 42%. But if we do some capture sequencing, it will be varied. And if the GC content is over 50%, maybe some microorganism contamination. So it's a very important quality control metrics. And then we do the risk filtering. As we see, this is the adapter. This adapter is used for the indexing and for the sequencing to be bound into the array. So when we use the reads, we need to remove these adapters. And then we got the pure insert fragment. And if the insert size is less than the sequencing length, the sequencing length is commonly used 150 BP. Then the read 1 or the read 2 will go through the insert size, and the adapter in the other side of the reads will be sequenced. This should be removed. And some reads of low quality, as I mentioned before, low Q30, or some reads to be too short, maybe less than 50 BP. These reads should also be removed. So when we removed all these low quality reads, we could see the ratio of the high quality reads to the raw reads, maybe more than 95%. And then we do the alignment and we mark for the duplication. When we got reads, we need to align to the genome to do the downstream analysis, such as the variant calling. And the first step is mapping, and then we remove the duplicated reads. This picture shows the duplicated reads. The duplicated reads means these reads may come from the same template. It means that they have the same information, so they need to be removed. Why we had duplication? Because this is an overview of the library building. We do the fragmentation, and then we do PCR for the introduction of the adapters. And during the PCR, we may introduce some duplicates, and some sequencer may introduce some duplicates. So the duplicates need to be removed. And here is some details of the removal of duplication. This is a duplicated, as the two reads is on the same orientation and on the same position. And also they should have the same Siga rate, Siga value. If they are on the different position, they are not a duplication, and the different orientation also is not duplication. And here's the Siga rate. The Siga value means the information of the alignment. The M means the alignment match, or can be sequencer match or mismatch. And I means insertion, and D means deletion. So if the reads have the same head and end, and they have the same Siga value, they will be marked as a duplication, as the conventional method do. But we have to do some optimization. We not only take the Siga rate, Siga value into consideration, we also take the mutation into consideration. So the duplicate rate may be lower than the conventional the method, and the sensitivity for the detection of variants will be higher. We need to do some quantity control for the insert size. As I mentioned before, if the insert size is too short, Then the read one will go through the whole insert fragment, and the adapter on the other side will be sequenced. It's a waste of the data. So the insert size at least should be more than 150 BP. And here's a picture from the insert size and the relationship between the enrichment efficiency, the capture efficiency. We could see that the insert size at 250 is the best for capture, and we need to have over 150 BP. So in here and here, the capture ratio I think is acceptable. What is the capture efficiency? The capture efficiency means that we got the reads from our library, and we want to the reads focused on our target. But how it focuses on our target is the capture efficiency. As we could see from this picture, the probe in here capture the target region, but if the target region is only partly matched to our probe, it also could be captured. So maybe some sequence not totally matched to our probe will also be captured. This we do not want this capture. So we need to calculate for the capture ratio, and the capture ratio should be over 60%. And commonly by our panel, the capture ratio will be over 70%. And another very important aspect of quantity control is the sequencing depth. And the sequencing depth is very important, as if we want the mutation to be supported by 4 unique reads after remove duplication, then we need very high depth. If we had a variant of 2% of frequency or even low, and we see in this picture, if we had 50 folds of the depth, and on the right of this dashed red line, the mutation will be detected, but on the left, it will be omitted. So as the sequencing depth increase, we could see that the part on the right is increased. And if we had more than 500 folds, then we had a confidence of more than 90% to detect the mutation. And if we had more, we could see that we had very high confidence to have this mutation to be detected with more than 4 reads. And if we want to detect for more low VIF of mutation, such as 0.2%, as we could see from this picture, we had 500 folds of sequencing depth, and we could see that we had very low confidence to detect such variant. And as the sequencing depth increased, we could see that if we had more than 5,000 folds of the sequencing depth, then we had more than 90% confidence to detect for such variant. And if we have 10,000, then we have near 100% confidence to detect for such variant. So in our panel for the tissue, we had more than 1,000 folds of the sequencing depth, and for cell-free DNA, we have more than 5,000 to allow for the detection for this VIF of variant. here is the quality control output from our system. And here is the total mapped data. The fraction of mapped data means the data to be properly mapped to the genome. And the fraction of properly paired, we use PE. So we have the fraction of the paired reads and the fraction of the duplication and the fraction of the targeted reads. It is the capture ratio. The capture ratio, we could see that it's near 80%. And the targeted data is around 5 gigabytes. And after remove duplication, we still have 4 gigabytes data. And here is very important, the average depth is around 2000 fold. And the average depth after we removed the duplication is around 1060 100-fold, and the coverage of more than 500 folds is very important. As I mentioned before, if we want to detect for the 2% VIF variant, we need to have the sequence depth more than 500 folds. It's more than 95%. And the insert size, because of the FFPE, may undergo some degradation, so the insert size is somehow short, and the Q30 is very high. Another very important quality control is for the sample contamination. As we know, the detection for the variant of cancer need to be of very high sensitivity, but if the sample is contaminated with other sample, there may be some false positive. So we need to do some quality control for the sample contamination, and we choose to use some SNPs of very high frequency of from 0.35 to 0.65 in all population. And these SNPs should not be leakaged. And we use the max mean likelihood for the calculation of the ratio of contamination. As we show in here, we had sample A and we had sample B, and they had different SNP. So when the sample A is contaminated with the sample B, the ratio of the base on the site of SNP will have some alteration as this. So based on this alteration, we could use some algorithm to predict for the contamination. We could predict the contamination as low as 1%. And let's see here a detailed example for the quantity control for sample contamination. And we had cancer type of colorectal cancer, and the sample is FFPE. And here is a sample is normally sample without contamination. And we could see this is the variant to be wild type, and their frequency is near 0. And this is the variant of is heterozygous, so their variants are near 0.5, and these variants of is homozygous, so their frequency is near 1. And here is a picture of sample contaminated by other sample, and we could see that in this point of the frequency is scattered. It means it's very different from this picture, and it may have some contamination. And we use the SNP to track for the sources of contamination, and we have found some variants in this sample and is present in the other sample, and by the SNP, we found this sample may be the source of the contamination. And we do the DNA extraction and the library building again, then the contamination is okay. When we had finished all the quantity control, then we do the variant detection for the somatic of the pair sample. And we had the tumor, the blood, we both do the sequencing, and we had the BAM file, and then we do the variant calling. We could have the somatic variant and the GeneMind variant from the tumor and the GeneMind variant from the blood. Then we exclude the GeneMind variant. Then we have the pure somatic variant. Here is a table of the commonly used software for the detection for somatic variants, the GATK, the VASCAN, the Mutate2, and we use the WABIC for variant detection. For variant detection, some other things need to be taken into consideration, such as the hotspot. The hotspot, what means the hotspot? The hotspot is some variants. It's very, very high probability to be seen on this kind of cancer patient. And we may have lower cutoff value for the detection. And the blacklist means we need to construct some background database for the error introduced by the library building or the sequence or some DNA extraction. So when we meet some background blacklist, we just remove it. And some VRF by the population, and if a variant has very high population VRF, it will be removed. For liquid biopsy, the variant detection is similar, but not all the same. We have the plasma for the cell-free DNA extraction, and we do the sequencing. And the white cell do the sequencing too, and then we have the somatic variant. We also need a hotspot and a blacklist. But another things we need to take consideration is the clonal hematopoiesis. We need to build a local database of clonal hematopoiesis. What is hematopoiesis? It is the somatic mutation from the white cell. And nearly every individual have this kind of mutation, such as this picture shows. These are some samples from normal people without tumor. They still have some variants to be associated with the cancer, such as ERBB2, the TP53, and F1. So we need to build this database to exclude these hematopoiesis. And we build some cell-free DNA background database as we need very high sequencing depth. We just want to remove the error from sequence, the library building, or some error from sample processing. So after we do this, we have these results output from our system, the genes, the location, the reference space, the auto base, and the depth, the mutation frequency, and the type of the mutation, and the HGVA's description of the mutation, the depth after removing the duplication, and the depth of the variant after removing the duplication, and whether it's on the hot site or in the repeat site. After we detect the SNV, we do the CNV detection, we map the reads to the genome, and then we could do the split reads or assembly or by the read depth. And the read depth is the most often used method for CNV detection. Also, we take the B allele frequency into consideration, and then we do the segmentation and we do the CNV calling. We use our in-house developed CNV detection software and 2.3 copies amplification could be identified. Here is the result output. This is a point plot for the BIF. And as we can see, the B allele frequency is shifted away from the base for the ERBB2. And the score calculated by the depth is also very high. So here is the CNV of ERBB2. And we will have a description of the CNV, the location, the gene, and the copy number. The SV, mainly the fusion gene such as ORC, is very important for the solid tumor. And the conventional method use the junction reads for the detection, and we had to do some optimization. So first we take all reads for the alignment, and then we collect these reads. These reads are not properly mapped to the genome, and then we mapped it to the target region and try to find the potential fusion reads, include the soft clipped or discordant paired end reads, and then we extract sequences from these and align them to the reference genome, and then we exclude some regions of homologous, and we build background baseline to exclude some potential error introduced by the sequencing. By using this method, we had higher detection rate for the fusion, as this is by our method, and we could see this is the breakpoint, and this is by conventional method, and there's nothing. So more junction reads could be identified, and the sensitivity for the fusion detection will be higher. Here's the result output of our system for the fusion detection, and here is the genes and their companion and the location of the breakpoint. And here's the IGV. Here is 2 breakpoints, the breakpoint 1 and the breakpoint 2. We could clearly see here's the junction reads. MSI is also very important after we had done the variant detection before. And the MSI is from microsatellites, and microsatellites are the repetitive sequences of 1 to 66 BP. So during the DNA replication, this sequence is easily to go strand shrinkage. It means that it's very easy to be expanded. Normally people, we just have one, but if the mismatch repairment is deficient, then we may have many these repeat sequences. So we could detect it by sequence and account for this repeat sequence. So this somatic size at the microsatellite will be calculated after we do the alignment, and we do the T-square test between the sample and the background database of the normal sample. and the percentage could be calculated as the MSI size and the total size. Besides, we had also built a background database for MSI of ctDNA. And here is the output of our system for MSI. We had this is the valid MSI site detected by the panel. And this is the site to be MSI, and here is the ratio, and here is the conclusion whether it's MSI high or is MS stable. So here is an example for MSI determination, and he is a patient of prostate cancer, and by the ctDNA we identify gene mutation of branch shift of the MMR genes, which is responsible for the MSI, and his MSI score is very high. You could see that the conclusion is MSI high. So he may have Lynch syndrome as he had a branch shift, loss of function mutation of MSH6. For TMB, we should use panel larger than 1 MB. It's recommended by the expert consensus. And here's a picture of the TMB from different types of cancer, and the mean value of TMB is around 3.5 MB. And the TMB age may be 10 mutation per MB. We use this workflow for the TMB determination. We had tumor and the blood, then we had the somatic variant. We just use the coding vision, we remove the driver mutation, and we had the non-synonymous mutation, and then we divided the mutation number by the region size, and we use the coefficient. We had do some regression between the WES result and our panel result. Then we multiply our panel result to some coefficient to get more accurate TMB value. And the HRD is very important for the ovarian, the breast, the prostate cancer, and the HRD. The full name is the homologous recombination deficiency. It could be caused by the BRCA1 and the BRCA2 mutation, or some other gene mutation, or some other reasons such as promoter methylation and some unknown reason. But for BRCA1 and 2, only near half of the patients could be determined as homologous recombination deficiency. So we need some other methods for HRD detection. At present, we could use the LOH, the TIA, and the LST for the detection for HRD. The LOH means the loss of heterozygosity, and the TIA, the telomeric anemia imbalance, and the large-scale state transitions. Let's see in detail. The loss of heterozygosity means in this region, the zygosity of the SMP will be homozygous. Some variant, some region is lost, and the homologous repairment could not repair it. So they had this LOH region. And we also look for the telomeric anemia imbalance. This means the imbalance near the telomeres, but there should not be some copy number variation. And for the large-scale state transitions, we need to have 2 copy number variation more than 10 MB, and their distance should be less than 3 MB. So this could be calculated as large-scale state transitions, but these could not be calculated as large-scale state transitions. So we designed for over 40,000 SNPs for the whole genome for the detection of HRD, and this SNP should not be linkaged with each other, and the HRR genes should be also included. And we use this workflow, the tumor, the normal white cell, and we built it by the depth of the SNP and the zygosity. The zygosity should not be wild type. And then we filter by the BLE frequency, and the filtering by the distance. It means that we trying to filter out the SNP that has possible linkage. And then we had over 20,000 SNPs for the HRD detection. We detect for the HRD both for the BRCA mutation and the HRD status. If a sample has very high HRD score, then it will be positive. But if it has BRCA mutation and the HRD status is negative, it also should be as positive. And if it has not BRCA mutation and the HRD score is very high, it's also positive. Here's an example, as this is ovarian cancer, and we do the HRD detection by the FFPE and the blood. We had HRD score of 54, and we had some TEL3 variants on the ATM, and we had VUAs. So these variants could not explain for the HRD, but we still have this sample to be HRD positive. And for MRD is another very important, but it's very difficult. MRD could not be found by the conventional radiographic method. And as we calculated, each cubic centimeter of the tumor lesion corresponds about 0.19 copies of tumor genomes. It's very, very real. And we need to have the ctDNA around 0.01 to 0.02%. And if we had 20 milliliter of the blood, of the whole blood from the patient, we may have 20 nanogram DNA, and 1 nanogram DNA contains 30 copies, 300 copies of DNA. So we had 1 milliliter plasma could have 10 nanogram of that DNA, and 3 to 4 plasma could be separate from 10 milliliter whole blood. So we could totally have 30,000 copies of cell-free DNA. So the valid sequence index need to be very high to detect for this VRF of mutation. We have 2 strategies for the MRD detection: the tumor-informed and the tumor-naive or agnostic variant or agnostic method. For the tumor-informed, we need to sequence the tumor tissue, and we identified some tumor-specific variant. We do the customized panel for this variant, and we do the MRD testing But for the tumor-naive workflow, we just sequence for the blood and to find for the tumor some tumor variants for MRD testing. So here is an overview for the features for tumor-informed and for the tumor-agnostic assays for MRD. And we could see that the tumor-informed has higher sensitivity, but it has longer turnaround time, and maybe it be somehow expensive. But we choose to use the tumor-informed workflow as it has very high sensitivity, and the sequencing cost is becoming low and low. So for MRD, how many sites should be included? The theoretical limit of ctDNA detection could be calculated by this equation. And by this equation, we could see that if we had more than 16 mutations to be used for MRD detection, then we had a very high confidence, near 100%, to detect the MRD. And we use for the UMI, the single molecular barcode for each fragment to improve for the sensitivity. And the whole big panel should be used for the identification. And as I have shown before, this is a picture for the tumor burden mutation. And we had a median count for MB is around 3.5. And if we want to have more than 16, we may to have a panel of more than 5 MB, more than 15 MB. So we could just use whole exome sequencing. And here is the result output for our MRD. And we could see it's a baseline before the patient undergo surgery or other treatment, and the maximum VIF is very high. The tumor fraction is also very high, but the first time point, the MRD is negative, and the second time point, we have detected some low VIF mutations, and the MRD is positive, just as this picture shows. Finally, let's see some variant notation and the interpretation principle. And we use this principle for the variant notation, the tail one, the variance of strong clinical significance. In this significant level of significance, the level A evidence means these drugs should be FDA approved and included in some professional guidelines, such as NCCN guidelines. And in level B evidence, some well-powered studies with consensus of expert is also okay. It's very high evidence. For the tail 2, the variant of the potential clinical significance, the level C, the FDA approved therapies for other tumor types, it could be also be considered. And the level D is some preclinical trials and for few case reports. So we mainly focus on the tail 1. And for the tail 1, here are some details interpretation. First is FDA approved therapies, and the mutation type may be activating the loss of function, the copy number variations, and some fusions. And the variant frequency may be most be somatic, and the population database had lower frequency, and some other database recorded as pathogenic. And for GeneMind variant interpretation, it may be somehow complex. The GeneMind for the BRCA, for the Lynch syndrome, as will be classified into pathogenic, likely pathogenic benign and likely benign. And in the middle, there is a variant of unknown significant VUS. So we use this information for the interpretation, the population data, the allele frequency, and some family-based segregation, and annotation, the prediction of the missense, the prediction for the inference indel, and some other database to know the function study or some other things to be associated with these genes or this variant. So at present, for the reporting and for the annotation, for the interpretation, we use this database. We use the COSMIC for the hotspot identification, and we use CLINVA for the pathogenic records for germline mutation and for the somatic mutation. And we use this GKB for the guidance for the chemotherapy. And we use NCCN and ESMO for the guidelines. So here is the first part of my lecture of the oncology pipeline. Thank you for your listening. And if you have any question, please ask. Thank you.
Thank you, Jackson. Very nice talk. So now we're waiting for any question before coming to on the audience question. I would like to ask you about the MRD. So do we have the IVD for the MRD solution?
I'm sorry. Do you mean the
IVD?
IVD, or you mean the IVD, the NMPA approval?
Yes.
For currently for solid tumor, there is no assay to be approved by NMPA or by FDA. The FDA approved only the MRD for the hematopoiesis tumors.
Yeah, okay. And then my second question also concerning about the initial before the surgery or do any further treatment. Do we need to have the sample before it? And
you mean for the MRD?
Yes.
Before the surgery?
Yes. Can you come back to the slide? Yeah. So do we need to collect the sample from patient like blood and the FFPE before do the surgery? And then after
yes.
Okay.
We could collect the sample in the surgery, but before the surgery is also okay.
So it means that do we need both germline and somatic mutation profiling before the surgery? Isn't it?
For MRD, actually we need for the somatic mutations, but if we sequence the blood, we also have the germline mutations, and we could use the blood to exclude for the germline mutation to improve the detection for the somatic mutation.
Okay. And so in recent years, we observe that the patient is have more than one type of cancer, and then the MRD to work with the patient with two different type of cancer or not?
If he had different types of cancer, I mean, for the method we used by the mutation, it may not be possible to distinguish which cancer is undergoing recurrence, but it could have some, some indications for the recurrence, but I cannot tell which cancer.
Okay, understand. It means that if they have more than one, the method doesn't work anymore, is it?
Yeah, if he had more than one cancer and you wanted to know which cancer is recurrence, may some other omics could be used, such as methylation sequencing.
Okay, thanks, thank you. So we have one question on the chat box. Anh ơi, em không hiểu cái câu hỏi của anh đó, anh có thể hỏi bằng tiếng Việt cũng được anh. Ở đây có bên chỗ của bên chỗ của GeneMind, SURAN Medical cũng support á anh hỏi giúp em bằng tiếng Việt được không anh? Em không hiểu. Anh Việt Beauty ơi, anh hỏi bằng tiếng Việt được không anh? Thì xong xuôi rồi tụi em hiểu rồi tụi em có thể dịch lại tiếng Anh được ở bên SURAN Medical. Ok, nếu mà ảnh không hỏi được thì không biết ai có câu hỏi thêm không nữa mọi người. Có ai hỏi không mọi người?
I have one question. Is the bioinformatic byline that you share is an open source for anyone, for a GeneMind user? Is it an open source or the pipeline, the bioinformatic pipeline that you introduced? Is it available for anyone, right?
Not totally. We have used some open source software, but some some in-house software has been developed by our bioinformatics team, and some optimization has done for our sequencer, so it may be not suitable for other equipment.
Okay, but so could you please summarize the key advantage of the pipeline for us for the clear understanding?
I'm sorry.
Could you please summarize or highlight any kind of like key advantage of the pipeline that you introduced for us to have more understand?
Yes, sure.
Sorry, let me translate in Chinese. 哎，罗伯，他就是让我们讲一下我们这个生性分析流程或者软件的一些关键的优势。
哦
对，
Okay. So for this pipeline we have validated by thousands of clinic samples. It has higher accuracy, and the system is fully automatic and easy to use. And the last but is very important. We had used some GPU speed up, so it will be very fast for large scale data.
Okay, thank you.
So we have one more question in the chat box. The question is between the tumor informed and tumor agnostic MRD strategy, which approach is more suitable for current hospital setting in Vietnam, or the one already adopted by your company, and why?
We choose to use the tumor informed because for tumor informed, it has higher sensitivity for the MRD detection. For we had real knowledge for the tumor mutation spectrum, but for the tumor agnostic, we need to build a very big panel or for the mutation, and for some tumor that its mutation spectrum is not highly specific. It means that he has a very broad spectrum of mutation. I think it's not easy for the tumor agnostic panel to detect for the MRD. The tumor informed is more suitable.
So em happy với câu hỏi của câu trả lời của Jackson chưa em? Em có muốn hỏi thêm?
Dạ, để em hỏi thêm.
Hỏi thêm.
So about the tumor inform is have a higher sensitive. So it's so maybe it's like it's suitable for maybe the tumor level is low, right?
Yeah.
And because of that, so that requires the tumor, and after that maybe that's the need to analyze it and to know that which type of the patients and which type of tumor they have with the tumor informed, right? And about the tumor agnostic, so it don't need the tumor, so it can adopt the ctDNA right away, so it could be faster. But I wonder that the tumor agnostic could be setting up in a hospital, in Vietnam hospital or not, because usually in the Vietnam hospital the cancer patient is a lot, and we don't really have time to do some small surgery to get the tumor. So whether that we could set up the tumor agnostic, and what the advantages of the tumor agnostic.
So the tumor agnostic has the advantage of quick turnaround time and maybe more convenient for some patient may the tissue or the is not available. But for MRD, I mean, if tumor agnostic panel to be used, I think just the SNV or indel is not enough, because the sensitivity, the problem of sensitivity, maybe
Right.
some multiple omics, such as methylation, and some other omics should be integrated into the SNV and the indels.
So if we only use the tumor agnostic, do we need to combine other method or other technique to make sure that to get a higher sensitive to diagnostic the disease, the cancer type?
Yeah, I think the other omics may be needed to improve the sensitivity. So it's a balance between the turnaround time, the convenience, and the sensitivity.
Well, thank you, Dr. Lu.
Because the MRD technique is not really widely used in Vietnam, so I would like to explain further in Vietnamese for my student. Can you come into the MRD slide, please?
Okay.
Yes, this one. Thank you. Mấy bạn học ở trong lớp á mọi người, thì tôi chưa có giới thiệu về cái kỹ thuật này. Cái chữ MRD á, viết tắt của chữ cái minimum residual disease, có nghĩa là giống như người ta muốn biết thử coi là sau khi mình điều trị ung thư á, thì liệu là ví dụ như mình phẫu thuật, mình cắt bỏ đi cái tumor đi, thì nó có relapse, có nghĩa là cái bệnh á, nó còn ở trong cơ thể mình không, cái tumor á, nó còn dư lại ở trong cái tồn dư tối thiểu á, mọi người, những cái tế bào ung thư đó, những cái tumor nó còn trong cơ thể mình hay không. Thì để làm được như vậy á, thì người ta sẽ lấy cái mẫu máu đó với cộng là cái mẫu mà cái mẫu tumor trước khi phẫu thuật đó mọi người đó, người ta đi giải trình tự trước để coi là cái bệnh nhân đó có những cái đột biến somatic đặc trưng nào của cái người đó mọi người. Có nghĩa là đều là một cái loại ung thư hết. Ví dụ như bị ung thư gan đi đó, thì người ta có cùng một ít đột biến, nhưng mà cũng có những cái đột biến đặc trưng cho từng cá thể đó. Thì người ta phải làm cái chuyện đó trước, xong sau đó rồi phẫu thuật xong rồi người bắt đầu người ta lấy mẫu máu đó để coi thử coi là người ta cũng đi giải trình tự tiếp để coi thử coi là cái đột biến mà somatic á, đặc trưng cho cái người đó nó còn ở trong cái mẫu máu của mình hay không đó. Thì tại vì cái tumor mình đã cắt đi rồi đúng không, mình không thể nào lấy tiếp tục nữa đó. Thì bởi vậy là người ta mới coi thử coi là nếu mà cái tumor đó nó còn ở đâu đó không biết đó trong cơ thể của mình, nhưng mà cái tumor đó nó sẽ tiết cái DNA của tumor đó vào trong máu. Bởi vậy là mình sẽ lấy cái mẫu máu để mình đi giải trình tự tiếp, mà giải cái độ phủ sau đó để tìm cái đột biến mà đặc trưng mà mình đã profiling trước đó đó, mình coi có hay không đó. Thì cái này là cái kỹ thuật nó gọi là cái chiến thuật, nó gọi là cái tồn dư tối thiểu là cái MRD cái gì đó. Thì ở đây thì mọi người cũng biết đó, là hồi xưa tới giờ thì mình cứ nghĩ là một người chỉ có bị một ung thư thôi đó, nhưng mà thực chất ra thì tôi thấy ở bên chỗ ung bướu thành phố Hồ Chí Minh đó, thì thấy là bây giờ là nó nhiều hơn một ung thư mọi người đó, và càng ngày càng nhiều đó. Một người không phải bệnh một ung thư không đó. Bởi vì nãy tôi mới hỏi là giờ liệu là cái kỹ thuật này á, thì có áp dụng được cho một cái người mà có hai loại ung thư như vậy đó, thì người ta nói không có được đó. Để làm cái đó thì phải sử dụng thêm mấy cái kỹ thuật khác như là cái omic khác như là DNA methylation đó. Rồi không biết là mấy bạn học viên có nắm được cái kỹ thuật này không mọi người? Hello. Ok rồi, không biết có ai hỏi gì thêm nữa không mọi người? Trời hỏi đi mọi người ta giới thiệu quá trời kỹ thuật hay luôn đó, người ta có nhiều giải pháp như vậy để mình có thể học hỏi thêm đúng không đó. Ở Việt Nam mình thì một số nơi cũng áp dụng nhưng mà không phải chỗ nào cũng áp dụng hết đúng không đó, thì người ta có giải pháp như vậy thì hỗ trợ mình rất là nhiều trong cái việc là ờ, điều trị cho bệnh nhân đúng không, bị ung thư các kiểu ở đây đó. Có ai hỏi thêm không mọi người? Rồi nếu mà không ai hỏi thêm nữa thì chắc là mình kết thúc cái chương trình ở đây. Kim ơi Kim,
Dạ em nghe thầy.
vậy là cái đã báo cáo xong cả hai phần luôn rồi đúng không em, hay là chỉ có một phần thôi em?
Dạ em thấy anh Chiến là gửi bên hai bản Bravo, hình như là chỉ mới xong cái ba like, còn cái oncology.
Dạ. Đã mới xong một phần anh ạ.
Dạ.
Ok rồi, vậy chắc là mình qua tới cái phần thứ hai ha. Thanks a lot Jackson, thanks a lot for your information, we learned a lot from your lecture, thank you so much. So now we come into the next section, yeah please.
Okay.
Ủa, Chiến là bạn Qin Lu này cũng nói tiếp luôn hả em? Nói cái sách.
Dạ.
Could you see my slides?
Yes, I can see the slide now. Can you make the full screen, please?
Okay. Okay, in the next part, I will have a brief introduction of our oncology solution. And first will be the guidelines for tumor NGAs and the solutions, and then the performance and some cases. And here is some guidelines and from the EMSO for the amplification for NGAs for oncology. And here is some clinic actionable for the non-small cell lung cancer for the EGFR or KRAS rate roles, and for the MATE ERBB2. So, and for a novel target as NRG1, so these genes should be all covered by the panel. And NCCN also recommended these genes should be covered in the non-small cell lung cancer. And for the advanced colorectal cancer, the KRAS, BRAF, MSI, KRAS, ERBB2, and the PLE should be covered. And the TMB, HER2 also recommended by the NCCN guidelines. And this also is the NCCN guidelines recommended the KRAS, NRAS, BRAF, HER2, and NTRK and the rate. So these targets should be covered, even the small panel should be covered, all these targets. And for the ovarian cancer, the HRD is recommended, as well as the fallopian tube cancer, the primary peritoneal cancer. This cancer HRD is recommended to be detected and to use for the PPARI treatment. And for some tumor agnostic genomic alterations, tumor agnostic means the pan cancer, means all the solid tumor could be used, such as the NTRK, the MSI, the rate, the BRAF, the FGFR123, and the TMB. But the TMB is not recommended measurement before we deciding to use the nivolumab plus the ipilimumab regimens. So if we do not decide to use this treatment, can be maybe not recommended. And here's the oncology solutions workflow I have shown before, both automatically and manually is supported. And here is our solid tumor panels for the 30 genes, 70 genes, 170 genes for all the solid panels, small panel, to cover all the targets, therapy targets, and a large panel of 580 genes. All these panels could detect for SNV, indel, CNV, and SV fusions, and MSI, and the FFPE blood, and some other liquid could also be supported. And here is the data volume needed, and all could be automated. And we had added some special design for the rows fusion partners, such as CD74, SDC4, SLC3482, and EZR regions. And the CNV, we could detect as low as 2.3 copies. And here we had contained the classic MSI set size recommended by the guidelines, and we had more than 100. Actually, we had 30 hundreds of the MSI size for MSI detection, and we had SMP for the cross-contamination quality control. Here is the automation systems for the library building, the DNA extraction, and the quality control and the pooling. In this machine, it is one machine could do the extraction, library preparation, and the QC and the pooling. All this could be done in this machine. And all this machine could be easily connected with the LIMS. And he's compatible with a broad range of reagents. And here is our sequencer platforms fully by ourselves. And FastSeq 300 is very fast, it's very suitable for the short turnaround detection. And the GeneMind M, a little bit big throughput, and the SubSeq 5000 has very high output, and it's suitable for WES, WGS, and some big panel. And the SubSeq Q, we had very huge output, and it could be used for the very big cohort research and a very big amount of samples. So for SubSeq 5,000, and for subsequent, they had very high data quality as Q40. And for these two platforms, it has Q30 over 85%. Of these platforms are suitable for cancer mutation detection. And also we had AIs for fully automatically integrated reporting, and all the pipeline and the reporting could be done automatically, or also could be corrected manually. And here are some details for the panel. The first is a small panel for lung cancer and the colorectal cancer. And we see we had these three platforms, different numbers of samples. These samples, this number is for tissue or for white blood. If we want to pair and we need pair samples, will be half of the numbers. And for this panel, we designed for lung cancer and colorectal cancers. We had 32 genes, and we had 12 fusion targets and more than 100 MSI sites. And we also include some chemotherapy targets of more than 50 genes comes from GKB database. And we had detection of limit of 0.2% for ctDNA and 1% for tissue. Here the performance, the sequencing performance of the panel, we had a very high mapping ratio, nearly 99%, and we had very high on-target rate of near 80%, and the coverage uniformity is also very good. We had very high of 0.1 for mean coverage. Here is the detailed targeted list, and we covered the targeted list I mentioned in the guideline before. All these genes have been covered. Also, we had covered some other genes may have the potential for therapies. Here's the demo report. This report could be fully automatically output, and we had the clinical information, and we had the result summary. We had 5 somatic mutations. We had 1 copy number variation, and we had 1 gene fusion. Also, we had a being gene. I will introduce for this gene in the next slides, and the MSI status. And here's the details of the variant, the therapies, and the potential therapies, and the class. So this would be the recommendation for the therapy, and the potential maybe if we lack of the therapies recommended here, we could take this into consideration. And this is the mutations description. So, and this is the copy number variation, this is fusion. And here's the MSI. Another is similar to the 30 gene panel, but is a little bit big. And over 70 genes is covered. We covered 76 genes with 15 genes fusion and the MSI genes of more than 100, and also the chemotherapy targets. And the data and the sample could be supported by our different platforms. So it has a high sensitivity as then as the small panel. And we had also the MSI, and we could have some probes for the cross-contamination identification. And here's the untargeted rate. We could see that it's also very high, and the coverage uniformity is also very high. Here's the detailed gene list of the lung and common cancer 70 gene panel, and this is the genes covered by all exon, and this chemotherapy targets, and some intra coverage. This intra coverage, as I mentioned before, is designed for the detection for the fusion, and the MSI sites recommended by the guideline and some other MSI guidelines. So the demo report is similar to I introduced before, so I just skip it. And we also had pan cancer 130 genes. This panel is designed for patients with solid tumor. All the targeted recommended by the guideline will be included. As I introduced in the background, the agnostic actionable targets all covered, except for the TMB and the HRD. And we had new 700 KB of the panel size, and we had different numbers of samples supported by different platforms. Also, these panels could be analyzed locally, and the reports could be generated automatically. All the solid path cancer are supported by this panel. And here's the performance of the panel. We could see that the mapping rate, on target rate, and the coverage uniformity is very good. And here is the detailed gene list. We had additional coverage for other solid tumor, and the initial coverage for the fusion detection. And the report is similar to the previous report. And we had a big panel of pan cancer. In this panel, we had over 580 genes. We covered TMB, MSI, and all the solid tumor is supported. And also the risk of mammalian cancer could be evaluated. So the FDA and NMP approved all the drugs of solid tumor is supported, and the MSI, TMB, and MR, and the PD-L1 or some hyperproliferation genes are covered. For this panel, it's relatively big. It's more than 2 MB for TMB detection, and for the fast-seq, we only, for FCM, the array, we only support for 4 samples, and for subseq or GeneMind, more samples will be supported. So he covered a broad range of the variants, and the LOD is for tissue is also 1%, and the LOD for ctDNA is also 0.2%. The mapping rate and the coverage of uniformity is very high. And here is the HRD panel. As I'm introduced before, the HRD, we need to detect for the LOH, TRA, and the LST. Also, we had 8 the solid tumor target for all the solid, such as the MSI and the fusion targets of all the solid tumors. So this panel will be some bigger than the other panel is over 4 MB, and T-shirt, especially powder T-shirt, is recommended. We need to be more than 8 gigabase for HRD detection, and here is the sample supported by different platforms. For large amount of sample, we recommended the sub-6 5000 for the HRD detection. And here is the HRD report. It's similar to the previous report, but with some description of the HRD. And here the MRD detection, we use the WES or some customized WES for HRD. For whole exome sequencing, we should have more than 35 gigabase, and for the small or optimized WES, we need more than 15 gigabase for each sample, and for white cell, we need 3 gigabase and 7 gigabase. Also, we have covered all the SNV, indel, MSI, and fusion and chemotherapy targets. For this panel, FastSeq 300 should use the biggest array, and for the GenoLab N and the SubSeq 5000, more samples are supported. But for MRD, if we have big cohort of sample, the SubSeq 5000 is recommended. And here is the MRD detection workflow. We had the block draw before surgery, and the MRD for the blood pre-surgery, and we had tissue and the blood in. Then we do the WES, and we do the MRD for the blood post-surgery, and after treatment, we do the MRD surveillance, and we do the follow-up 3 to 6 months. And we need a 20 milliliter blood by cfDNA blood tube. This is a demo report, and we could see before. Here's the description of the patient, and here's the MRD summary. The baseline, the first time of MRD detection, the second time of MRD detection, and any other detection of MRD of the follow-up. And this picture of follow-up will be drawn. And also the clinical action, the annotation of the variants will be outputted, and as the variant details, the therapies recommended, and the class. So let's see some performance. The first, we use some reference materials for the performance verification, and we use the standard substance 1 and the standard substance 2 of these variants. These are some variants that often being detected in the solid tumor, and we had a broad range of the frequency. For this detection, we have validated the detection on different platforms of GenoLab M, FastSeq 300, and SubSeq 5000. We could see that all these mutations could be detected. And we had validated our panel by some NMPA or Chinese FDA approved kit. As we could see, we are validated by the L858R and the 19-del, the ERBB2 insertion, and the ORC fusion, and the ERBB amplification. This was validated in the lung cancer, and this validated in the breast cancer. As we could see, our panel had a concordance rate of the 100% compared to the Chinese FDA approved kits. And the detection rate for non-cancer, we have over 5,000 samples. And for EGFR, we have 50%. And for the tissue, we had 53.8%. For the ctDNA, we had 41.3%. And from the expert consensus, we could see that the overall ratio of the EGFR mutation is around 50%, while the 19-DAR compromise around 45%, and the L858R compromise around 40%. And our detection rate is very similar to the detection rate mentioned in the expert consensus. And the detection rate for the colon cancer, we could see that the overall of KRAS mutation is around 40% reported by some big cohort, and our detection rate is very similar to the big population data. And here's the TMB. The TMB, we need to construct some comparison between the WES and the panel. And we do some regression, and we could see that in the non-cancer and the colon cancer, the correlation between the panel and the exome has good correlation. This is a picture from FDA approved panel of PGDX helical tissue. And for HRD, we had validated for some samples from BRCA positive. And we could see that BRCA positive samples had all very high HRD scores or positive. Here is an example of the positive. And here is an example of the negative. So all the HRD positive caused by the BRCA could be properly detected. And for MRD, we had tests for some standard substance of low VIF of 0.02, and we could see that all these mutations could be detected by our MRD panel. Here are some clinical cases, and this is a diagram of the resistance of EGFR TKI. As I see the mechanisms of the second generation EGFR TKI would be the primary resistance and the acquired resistance. The primary resistance could be the EGFR exon 20 insertions and the being deletion polymorphism. And the acquired resistance could be some altered EGFR signaling pathway, such as the C797S mutation and some other mutations. So in this case, we use the liquid biopsy for the monitoring of some drug resistance. And in this patient, he received liquid biopsy after chemotherapy, and we could see the VIF of the EGF PL858R and the TP53. After chemotherapy, the cell-free DNA VIF is not very high, and after 4 months, he had progression, and we could see that the VIF of this variant increases. And then he received osimertinib, and it works. we could see the VRF of mutation decreases, and then we do the surveillance, but he got progression, as we could see that the VRF increases. And very importantly, he had B deletion, and he had RB and TB53 commutation. So, and based on the historical picture, he may have the small cancer cell transformation. And the beam depletion is associated with the primary resistance to the EGFR DKI, as we see from this picture. If the patient had BIN depletion, he had worse survival. And the EGFR RB1 and the TP53 mutations is associated with worse survival. As we could see in this picture, if the patient had these three mutants, they had the worst survival. And for this patient, finally, he had no drug available. So finally, unfortunately, he got progression. And for case 2, in this case, he had tissue to be sequenced by our lung and common panel, and he had 19 del. Then he received gefitinib, and he had resistance. Then he had ctDNA liquid biopsy. They found some other variants. Then he received osimertinib, and he had resistance. And ctDNA and found some heterogeneity. So let's see the detail. Firstly, he had 19 del, and he could receive for the gefitinib. Then he got resistance, and we found he had amplification of EGFR, and he had very complex spectrum of this variant. And we could see this T790 and L792H, and these variants accumulated in this location. So based on these findings, we had these mutations are very frequently to be seen associated with the osimertinib drug resistance. And based on the variant we found in our results by liquid biopsy, we have drawn the heterogeneity or evolution tree by this. Firstly, he had 19 del, and then he received gefitinib, and he got to had T790M to got the resistance for gefitinib, and then he received osimertinib, and he had 19 del and T790M, or 19 del and T0M plus G796S. We notice that all these mutations are not located on the same cell, as they are not located in cis. You could see that they are not on the same reads, so they may be in the different cancer cells. So we draw this. The cancer has very different evolution. And if there have any possible overcome strategies for this mutation, unfortunately, no. For the 79S in cis with T790M, bractinib and certezumab may work for this, but for the other mutation, no currently targeted therapy is available. So this is the brief introduction of our oncology solution and some cases. Thank you for your listening. And if you have any question, please ask. Thank you.
Thanks a lot for a very informative lecture. So before waiting on the question, I would like to asking about I saw the example, some K report, very interesting K report. I just wonder that if we don't have the NGS technology for profiling on the mutation in the cfDNA, the treatment for the cancer efficient enough compared to the without the NGS. How do you think? If we don't have the NGS, you have to select the drug, the treatment, and then how the patient were treatment. So I just wonder that if we have the technology, this technology, have it efficient or not efficient.
I'm sorry.
For example, in case that we cannot profile, if we don't have the NGS technology to help us to profile the heterogeneity of the patient sample. Over here is the ctDNA, and then the treatment can work well. It means that we can prolong the survival of the patient. Or in case that we have this technology, we also cannot help the patient a lot, and we spend a lot of money. I just want to make sure that we spend a lot of money to do the sequencing and then profiling the mutation for the patient, and it helps to extend or prolong the survival of the patient. If we don't have NGS, it means that we cannot profile the mutation. The patient, it can survive longer or not.
Okay, let me have a repeat. You mean if we sequence the ctDNA and to guide for the treatment, and if the patient could have longer survival?
Yes. So in case that we don't sequencing, and then how do you think the patient can survive or not survive? Because like to do the kind of sequencing, we to spend a lot of time for individual patient, and we also spend a lot of money to do sequencing and time as well, and then it help the patient survive compared to the survival of the patient without any care from the sequencing.
Based on some clinical study, when the ctDNA or some sequence guide treatment, maybe I can say some patient positive for some variant could have benefits from some, some targeted therapy. But if we don't do the sequencing, we just treat all the patients for the targeted sequencing, I think maybe some also could have the benefits, but we could not, pick up the patients who could have more or higher probability to benefit from the drugs, and maybe this could be a save of money and time. If we do not have the NGS, and some people which are not suitable for the targeted therapy have received for the therapy, then some money is wasted.
So in general, the sequencing over here, the NGSE can have a lot of patients for have to select the drug for them. Okay, thanks a lot.
Yes.
Có ai hỏi gì đâu mọi người? Tôi chỉ thắc mắc là như tại vì mình phải làm, mọi người cũng thấy đó, nó có nhiều giai đoạn, giống như uống thuốc xong xuôi rồi á, rồi cái lại kháng, rồi mình lại sequencing lại, đúng không? Đó thì tôi cũng không biết được là cái việc mà mình cứ sequencing giống như vậy đó thì tốn nhiều tiền, mà không biết được là nó có hiệu quả trong cái việc là giúp cho bệnh nhân có cái sống còn nó dài hơn so với cái người mà thí dụ như mình không cần sequencing, mình cứ theo guideline, mình cứ cho uống thuốc nó gì đó, thì không biết cái nào là mọi người cũng thấy đúng không? Ở trong đây nè trình bày là cứ uống thuốc xong rồi lại có đột biến mới, rồi kháng thuốc, rồi lại đổi thuốc đó, thì mình cũng cảm thấy là tốn rất nhiều tiền của luôn mọi người, mà cái này là chăm sóc cho từng cá thể. Có bệnh nhân K1 nó đột biến khác với K2, mọi người cũng thấy đúng không? Đó có nghĩa là bác sĩ phải chăm sóc với từng cá thể, và lên cái lộ trình chăm sóc nó cũng chuyên biệt một cách rất là cụ thể luôn á, mọi người cũng thấy đúng không? Tại vì cứ phải theo dõi đó gì đó cho từng cá thể chứ nó không có chung mọi người, ở đây là cá thể hóa trong điều trị đó, thì không biết được là mình tốn nhiều tiền, mình cứ theo đuổi cái sự đột biến nó như vậy á, thì nó có hiệu quả hay không, đúng không? Đó ví dụ như giờ mình tốn quá trời tiền mà chỉ kéo dài thêm được 1 tháng ví dụ vậy đó, hoặc là 2 tháng, thì không biết là liệu là mình có nên làm không, đúng không? Đó tôi hỏi vậy thôi chứ tôi không phải là bắt buộc là không nên làm nha mọi người ha. Giống như mình thấy á, mọi người cũng thấy đây đó, nó cứ đột biến mới đó là mình phải dí theo nó vậy đó.
Dạ, em xin có một ý kiến nữa về cái vấn đề mà anh Lợi có nói về cái vấn đề mà mắc ấy ạ, tốn chi phí ạ. Thì thực ra nó sẽ phụ thuộc vào chiến lược giải trình tự của mỗi một lab hoặc là của mỗi một 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 phòng xét nghiệm ấy ạ. Ví dụ như nếu như mình mà xài những cái hệ mà nó có công suất nhỏ ấy, ví dụ như Dr. Lu, can you back to the summary of the GeneMind panel slide?
Okay.
Mọi người để em nhờ. Can you... Okay. No.
Okay. This one. This one.
Next one. Next one. Next. Please next.
Slide
Next.
number, slide number is the best. Em cho cái số slide em để cho ông chỉ cho nó đúng chỗ.
Em không nhớ. Please next 2 more slide.
罗伯往下翻。
For some summary of the number of sample per pro cell of each sequencer. Next slide, please.
就
Okay.
是有
Dạ, đây em lấy ví dụ ở đây thì ví dụ như nó sẽ phụ thuộc vào chiến lược giải trình tự của mỗi lab ạ. Thì anh có thể thấy ở đây có thể là GeneMind hoặc là các nhà sản xuất khác cũng vậy, thì nó sẽ có những cái máy có throughput từ nhỏ cho đến lớn. Ví dụ như nếu như mình mà giải với cái panel, ví dụ panel nhỏ chẳng hạn, và mình áp dụng những cái hệ thống giải trình tự nhỏ thì như anh Lợi nó sẽ rất là mắc. Nhưng mà nếu như mà mình có đủ cái mình có thể collect được đủ cái lượng mẫu á, và mình có thể, em lấy ví dụ như giải trên hệ thống sắp xích 5.000 chẳng hạn, nếu như mình có thể gom được mẫu thì có thể là với cái flow cell lớn thì có thể là cái giá có thể down xuống khoảng tầm 2,5 đô trên 1 GB dữ liệu, với cái hệ thống mà hiện nay tụi em đang offer là cái hệ thống lớn nhất là sắp xích 5.000 chẳng hạn. Thì em nghĩ là cái việc mà mà để giải trình tự đi giải trình tự lại như anh Lợi còn Sơn thì cũng 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 sẽ không phải là vấn đề mà quá là khó khăn về mặt chi phí với người bệnh, cũng như là cái chi phí nó sẽ phù hợp hơn với các lab. Nhưng ví dụ nếu chúng ta không gom đủ mẫu mà ví dụ chúng ta giải mẫu plasma với cái hệ thống nhỏ, ví dụ có 4 mẫu một cái flow cell chẳng hạn, thì có thể giá nó rơi đến vào khoảng 20 đến 30 đô trên một ghi dữ liệu, thì lúc đấy thì nó sẽ rất là mắc và tốn kém chi phí so với người bệnh. Nên thành ra là theo em nghĩ là sẽ phụ thuộc vào cái chiến lược giải trình tự và cái số mẫu của chúng ta có thể gom được hay không ạ.
Hiểu rồi, cảm ơn Chiến rất nhiều. Thì kỹ thuật giải trình tự mọi người thấy cũng dần dần cũng rất là rẻ đúng không? Đó,
Dạ.
tại mình giải số lượng lớn thì cái việc mà giải trình tự nó không còn là một cái vấn đề mà nó giống như hồi xưa đúng không?
Dạ.
Rồi, không biết ai hỏi gì nữa không mọi người? Thoải mái hỏi đi mọi người. Ở đây là cái cơ hội để mình trao đổi kiến thức thêm đúng không? Qua cái bài buổi hôm nay mọi người thấy là người ta đi nhanh lắm luôn rồi đúng không? Đó là tại vì ung thư nó đi nhanh thì giờ mình phải theo nó thôi, mình cũng thấy đó, nó cứ đột biến liên tục, uống thuốc rồi lại đột biến mới rồi nó kháng thuốc đó, rồi phải thay thuốc rồi xong xuôi rồi lại phải giải trình tự để kịp thuốc để thay sao cho nó phù hợp đó. Thì ung thư nó đi nhanh thì giờ cái kỹ thuật của mình cũng phải đi nhanh đúng không, cũng phải rẻ đi đó để có thể giúp điều trị một cách hiệu quả đó. Chứ hồi xưa là tụi tôi làm tụi tôi không nghĩ tới là mình có thể làm được ở mức độ này luôn mọi người đó. Tại hồi xưa ví dụ như giải 30x thôi, một cái mẫu whole genome sequencing là tới 1.000 đô hơn đúng không, đó cách đây 5 năm đó gì đó. Nhưng bây giờ thì rẻ quá rồi đó, mình có thể là giải quyết những cái vấn đề mà nó thay đổi liên tục của những cái tế bào ung thư đó, nó gây đột biến và thay đổi liên tục. Rồi không biết có ai hỏi gì nữa không mọi người, hỏi đi. Cái bài rất là mới đó, quá trời thông tin mới đó. Em Sơn em cứ bật cái microphone lên em hỏi Sơn đó, em đọc luôn giúp giùm tôi ha, đừng có ngại em.
I have a question for you. So you're talking about the 580 panel. So the 580 panel is designed for the pan cancer use. So my question is, in practice, which cancer type are most commonly tested using this panel?
You ask for the big panel, the 580 genes panel.
Yeah, 580 panel.
And which tumor is the most suitable to use this panel?
Yes, and in practice, which cancer type is usually detected by this panel?
Okay, this panel was designed for all the solid tumor, and based on our experience, we use this panel. The most tumor we use this panel for is the non-cancer and the colorectal cancer, and also the breast cancer, the prostate cancer, and the bladder cancer. It also could be used, but I think it's difficult to say which is the most suitable, as this panel may be suitable for near or the solid tumor. And I think the most cancer to be used for maybe the colorectal cancer and the non-cancer. That's it.
Thank you. And my second question is, so is the 580 panels is contain a lot of genes, and could it be possible is to alternate to the whole genome, the whole exome, or the whole genome sequencing in clinical practice? Could it be just only use the 580 panel, and we don't need to use the whole exome or whole genome sequencing?
Okay, you mean use this panel instead of whole exome or whole genome sequencing for tumor?
Right.
Okay, I think this may not be clinical use, just for research use.
In clinical use.
In clinical use, I think maybe WES and the whole genome sequencing is not a very appropriate choice, because if we use whole exome sequencing and the whole genome sequencing, as I mentioned in the first slides, we need to have the sequencing depth of more than 500 folds for the detection for the variant of the frequency of 1%. So if we use WES and the WGS, we need to have very high, very big data amount. If we use the whole genome sequencing, we may for 500 folds, we may need for 500, I think 19. We may need 1 TB data amount. It's very expensive, and the analysis for this data will be very slow, and the turnaround time will be very long, and it's very expensive. As the same for whole exome sequencing for the routine clinical use. So for the routine clinical use, I recommend it for the small panel, relatively to the WES and the WGS, such as the 580 genes panel, or even smaller. If you don't plan to use the immunotherapy, you could just use some small panels such as 130 genes. It's more cost effective, and the turnaround time will be more short.
Right, like due to the large data storage, so it's maybe slower our analysis. So you suggest that we should use the panel, the 580 panel, rather than the WES or WGS, right?
Yes,
Yeah.
because
Okay. Thank you.
I have a question that I would like to know how about the situation in China. Which panel is the you show that you have some panel 30 panel and 70 or bigger, small and large panel, and how in the China in China use the panel, and which panel is most popular in China, and when the doctors recommend the which panel for can you show some example when doctor use the small panel and when doctor use the large panel?
Okay. In most of the situation, I mean, the small panel is recommended, especially for the 30 or the 70 panel, because it's cheaper, and in the hospital, the big panel could be much expensive. So we had taste the most sample. Most of our sample is based on the small panel, and for the 580 this big panel, when the doctor want to use some immunotherapy based on TMB, he will recommend it for this panel, or he had received the small panel, but nothing is found. So he had no drug associated variant. Maybe the big panel will be recommended. But at most situation, I think the small panel is more popular.
And do you think in the future, the big panel may become popular in China or not?
In the future, I think the big panel will be more popular in China because the cost of the sequencing is becoming more and more lower, and the cost for library building, I think, is similar between the big panel and the small panel. Just the sequencing data amount matters.
Yes, thank you for your information.
Thanks a lot.
You.
Very informative. Có ai hỏi gì nữa không mọi người? Rồi, không ai hỏi gì nữa thì cảm ơn mọi người đã dành thời gian ra. Cảm ơn speaker rất là nhiều. Cảm ơn SURAN Medical đã mời mấy speaker từ GeneMind đó để cung cấp những cái thông tin rất hữu ích cho mọi người. Thanks a lot for your time, Dr. Qin and also Jackson. We today have a lot of information, have a lot of new technology, new solution for cancer therapy. Thanks a lot. We learned a lot from your lecture. Thank you so much. Also, thank you, SURAN Medical, that invite a very nice speaker from GeneMind in order to give us quite a lot of information, a lot of new technology and solution. Thank you so much. So we ending here, yeah, and hopefully we will meeting in the other solution from GeneMind as well, yeah, in the future. Thank you so much again.
Thank you.
Rồi, xin chào mọi người ha. Cảm ơn mọi người một lần nữa đã dành thời gian ra tham dự cái buổi này ha. Cảm ơn mọi người. Chào mọi người ạ.
Dạ, xin chào mọi người ạ.